Okay, so you have the handout in front of you there, 4.6 net force. Let's just sort of go through this a little bit here. And basically the key idea for the whole next couple of days is the net force has to be 0. And really what we're trying to do is find out the force that will cause the net force to be 0. In other words, the whole thing's in place. Okay? And that force that keeps everything in place is called the equilibrium. So, in the absence of force, objects at rest stay at rest, and objects in motion continue in motion. More specifically, in the absence of a net force, objects do not change their state of motion. For example, if you push with equal and opposite forces on opposite sides of an object at rest, it will remain at rest. So the forces cancel each other out, and there is no net force. It is the net force that changes an object's state of motion. Figure 410 over here on the right shows how forces combine to produce a net force, and this is all basically a review, right? When you pull horizontally with a force of 10 newtons on an object resting on a frictional surface, the net force action on the object is 10 newtons. If a friend assists you and also pulls in the same direction with a force of 5 newtons, well then the net force is the sum of the forces of 15 newtons. The object moves as if it were pulled with a single 15 newton force. However, if your friend pulls with a force of 5 newtons in the opposite direction, the net force is the difference, or 5 newtons, and so on, right? All pretty much review for you guys. I'm just sort of reminding you some stuff. Okay, here's the key part. Equilibrium, when net force equals 0. What forces act on your book while it's motionless on a table? Don't just say it's weight. If only the force of gravity were acting on the book, it would be in free fall. The fact that the book is at rest is evidence that another force must be acting on it. This other force exactly balances the book's weight and produces a net force of 0. The other force is the support force of the table. Support force is often called the normal force, and you've learned about that already. As shown in figure 411, the table pushes up on the book with a force equal to the book's weight. When an object is at rest, with the net force on it being 0, we say the object is in a state of equilibrium. The resting book is in equilibrium. Does the table really push up on the book? And I've had discussions with students in the past with this, almost arguments. Well, certainly arguments. It never came to fisticuffs, but he was adamant there was no upwards force. And of course, I was equally adamant that there would be. I won. Yes, just as the spring pushes up on your hand when you compress it. Look at figure 411. You can feel the spring pushing back on your hand. Similarly, a book lying on a table compresses the atoms in the table. Behaving like microscopic springs, the atoms in contact with the book push back on it. Since the book is in equilibrium, the net force on it must be 0. The table actually pushes up on the book with the same force that the book presses down. An ant trapped between a book and a table would feel itself being squashed from both sides, the top and the bottom. When you hang from a rope, the atoms in the rope are not compressed. Instead, the atoms are stretched apart. A tension force is established in the rope. A rope under tension twangs if you pluck it, like a guitar string. How much tension is in the rope when you hang from it? If you are in equilibrium, then the tension must equal your weight. You might want to highlight that. That's an important one right there. Where's my highlighter thingy? The rope pulls you up and the force of gravity pulls you down. Since the equal and opposite forces cancel each other out, you hang motionless. So this normal force that we've dealt with up to now is really an equilibrant. More about that very soon. Suppose you hang from a bar supported by 2 ropes, as in figure 412. Neglecting the weight of the bar, the tension in each rope is 1/2 your weight. How come half? 2 of them, exactly, right? So if the weight force is, say, I don't know how heavy this person is, we'll say 300 newtons, well then the tension here is going to be 150 and the tension here is going to be 150. They have to combine together, which of course is why if you've got, multiple ropes, you've got, less tension on them, they're more likely to break. The people at the Hyatt Regency would have preferred if there had been more rods holding those walkways up, right? Less tension in them. Can you have tension you can have tension in a rope or a wire, but can you have tension in a rod? Absolutely. Okay, you can have tension and you can have compression. The total tension force acting upward, half your weight plus half your weight balances your weight, which acts downward. When doing pull-ups using both arms, each arm supports half of your weight. Have you ever tried pull-ups with just one arm? Why is it twice as difficult? Like, a lot of people can do this, chin-ups, right? But with one hand, can you do it? I can't. I'm feeble. Okay? Because I need one arm to pull all my weight up. A spring scale can also be used to measure tension. When we weigh a bag of apples by suspending it on a spring, The scale reading us tells the weight. Consider a 1 kilogram bag of 10 apples weighing 10 newtons. When suspended by a single vertical scale, as shown on the left in figure 413, the scale reads 10 newtons right here. But if instead we hang the 10 newton bag from a pair of vertical scales, as shown on the right in figure 413, each scale reads only 5. The two scales pull up with a combined force equaling the bag's weight. Since the bag hangs at rest, the net force on it must be 0. Key concept is this: if a 10 newton bag is in equilibrium, the resultant of the forces applied by the pair of springs must equal 10 newtons. If the spring scales are oriented vertically, straight up and down, this is 5 plus 5 or 10 newtons. What happens if you put it at an angle? Let's now consider non-vertically oriented spring scales. In other words, they're at an angle. The tension is greater in a pair of non-vertical spring scales and depends on their angle from the vertical. This more complicated situation is most easily understood using our old friend, vectors. Yay, vectors have returned. Well, they've been all here all along. Recall our treatment of velocity vectors in Chapter 3. We'll now use the same vector addition techniques with forces. Force like velocity has magnitude and direction as an vector quantity. Look at the left of figure 414 right here. Notice that when the spring scales hang at 60 degrees from the vertical, their readings are 10 newtons each, double the tension of the vertically hanging scales. Why? Because the sum of the two tension vectors must support the downward acting 10 newton weight. The sum of the vectors must be 10 newtons, directed vertically upward, as shown by the diagonal of the parallelogram formed from the vectors. And they're kind of talking mumbo jumbo, right? What they're really saying is this, and you can draw this in, right? If this is 10 newtons right here, right? This tension right here has to be 5, and this tension on this side must be 5. And if the vertical components are 5, then what's the hypotenuse going to be? Well, greater than 5, which is why the spring scales show a greater thing. And as you go wider and wider and wider, here I went to 75, the spring scale will actually show 20. Okay? Because again, that has to be 5. Oops. And it's just simple trigonometry that tells you why this is so much greater. So back to my point about getting it perfectly flat. Could you ever get it perfectly flat? Because if you had it perfectly flat, then what would be the vertical tension here? 0. And it wouldn't hold it up. You have to have some even tiny, little teeny angle. There has to be some vertical component so that it can be balanced by this. Does that make sense? Give me a nod. I feel like I'm losing you. Yeah? Notice on the right of figure 414, the angle from the vertical is increased to 75. At this angle, each spring must pull with 20 newtons to produce the required 10 newtons vertically upward result. As the angle between the scales increases, the tension in the scales must increase for the resultant to remain 10 newtons. In terms of parallelogram, as the scale's angle from the vertical increases, the magnitude of the tension force must also increase for the diagonal to remain the same. Blah, 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 blah. I did a better job explaining. If you understand this, you understand why a vertical clothesline can support your weight, but a horizontal clothesline cannot, right? You don't see too many clotheslines out there anymore, but as a kid, you might have, grabbed hold of one and hung on it, right? Eventually, as you get older, it's going to break. Okay? You could probably, if you tied it from a tree, you could probably swing from it. It's got enough tension capability in it. But if you put it horizontally, then that vertical component is going to be greater, right? It'd be like this kind of thing, right? You would need that vertical component to be half your weight. This tension here is going to be more than the wire can hold. For any pair of scales, ropes, or wires supporting a load, the greater their angle from the vertical, the larger the tension force in them. The resultant of the tension forces, or the diagonal of the parallelogram they describe, must be equal and opposite the load being supported. As you'll see when you're asking following questions, the parallelogram technique of adding vectors yields some interesting results. Well, I don't know about that. Let's try some clicker stuff. So question number 1, when you step on a bathroom scale, the downward force supplied by your feet and the upward force supplied by the floor compress a calibrated spring. The compression of the spring gives your weight. In effect, the scale measures the floor's support force. What will each scale read if you stand on 2 scales with your weight divided equally between them? Like so.
It says I got every question.
Yeah.
Oh yeah? Well, smarten up. I must have hit stop. Sorry, I must have hit stop. Okay. So read What will each scale read if you stand on two scales with your weight divided equally between them? Will it be your original weight? Will it be your original weight divided by 2? Will it be your original weight times by 2? Or are you not sure and just copying out and entering D? What happens if you lean into one side? Will the scale you're putting more weight show more? Will the scale you're putting more weight show less? Will they still show equal weights if your weight divided by 2? Or will they still show your original weight? Well, you tell me. Punch it in. 100%, yay, you get it. Yes, it's going to be your original weight divided by 2. B. It's going to be A. The scale you're putting more weight on will show more, right? You're leaning into it. I don't know. Who put B? I can check later. Which one's more likely to break? B is way more likely to break because of that tension thing. B. And is it possible? No, not possible. In fact, you can't even get, a guitar string you might be able to get pretty horizontal, right? But if it's long enough, like think about hydro wires. Do they not sort of go like that?
Are they not supposed to go like that then?
How come?
Because when the ice freezes and then they'll compress and so they'll break.
If the ice freezes on there and adds more weight, if they are perfectly straight, then that adds that weight and it's going to put more tension. So they are slack like that so that there is an angle so that there becomes less tension.
Singularity.
Pardon me?
Would be space singularity in the middle of the
A singularity.
platform.
Oh, no, don't do that. Don't do that. Okay, so yeah, here's where I usually talk about the Roman arch. Here's a picture that I took in Turkey a few years back, and I said, oh, hey, I gotta take a picture of that and show my physics class. So I did. I thought that was pretty cool. It's like a 2,000-year-old arch. There's that one there, and then the next one here, I think. Is there a second one? Oh yeah, there's even older ones. Okay, same idea. It could be my, well, I don't know. I don't recognize those sunglasses, I'm not sure. We were on a tour, so. And there should be one, is there another one here? Yes, this one I always think is cool because you can actually see, can you see the daylight there? You can actually see that there's nothing holding it together, it's just physics kind of holding it together. And those are like probably 3,000 years old. Okay. I guess that's it. I thought there was another. Okay, so you already know one example of force in two dimensions. This is basically the same kind of information, but it's more mathematical oriented. When friction acts between two surfaces, you must take into account the friction force that's parallel to the surface and the normal force perpendicular to it. So far, you've considered only motion along the surface. Now we'll use your skill in adding vectors to analyze situations in which forces on an object or at angles out of 90 degrees, blah, blah, blah. Equilibrium and the equilibrium. There's that word finally. The equilibrium. An object is in equilibrium when the net force on it is 0. When in equilibrium, an object is motionless or moves with constant velocity. According to Newton's laws, the object will not be accelerated because there is no net force on it. You've already added two force vectors to find the net force of 0. Equilibrium also occurs when the resultant of 3 or more forces equals a net force of 0. Figure 1a shows 3 forces exerted on a point object. What is the sum of A, B, and C, or what is the net force on the object? So if I were to actually do this, and I'll just redraw A, B, and C here with different colors. If I were to take A, and then B, and then C, and then I'm going to move them away and I'm going to put them all tip to tail, where do I end up? Right back where I started, which shows that the net force is equal to 0. I didn't go anywhere. Figure 1b shows the addition of 3 forces, A, B, and C. Note that the three vectors form a closed triangle. There is no net force, so the sum is 0, and the object is in equilibrium. Is it moving?
Maybe.
Correct answer is maybe. Where was I? Suppose 2 forces are exerted on an object and the sum is not 0. How would you find a third force that when added to the other 2 would add up to 0? So that's what we're talking about here. If I've got an A and a B and I don't know C, C is called the equilibrium. C is the one that puts it in equilibrium, makes the net force 0. Okay, if you only know A and B. Such a force, one that produces equilibrium, is called the equilibrium. There's the key term right there.
Is C always going to be the one?
No, I mean, I'm just saying in this particular case, right? A could be the equilibrium, right? They're just arbitrarily labeled, right? But it's the force. If you've got two and it's not in equilibrium, then it's the third one that produces equilibrium. It could be the fourth one, it could be the fifth one, it could whichever one makes the sum of all the forces equal to 0. To find the equilibrium, first find the sum of the forces exerted on the object. That is called the resultant. The single force that would produce the same effect as the two individual forces acting together. And here it is here. The equilibrium is thus a force with a magnitude equal to the resultant, but in the opposite direction. That is the thing you want to highlight. Okay, so you basically add the vectors, find the resultant, and then all you do is change the direction. That's how simple it is. Figure 2 illustrates this procedure for two vectors, but any numbers of vectors could be used. So here we have A and B. A and B. We're going to add them tip to tail. We're going to add them A plus B tip to tail. This is my resultant. Okay, and once I've got that, then I simply rotate it 180 degrees, and that is known as the equilibrium.
So,
It's the exact same length as the resultant, just opposite direction. The equilibrium is a force with a magnitude equal to the resultant, but in the opposite direction. Well, you'd show the resultant, and then you'd write, therefore, the equilibrium is, and you just change the angle, right? Like if it's like, say this one here is, if R is, say, 100 newtons at, we'll say, I don't know, what's that, north, maybe 20 west, then we use the letter E for equilibrium. It would be 100 newtons. Instead of north 20 west, it would be south 20 east. It's really that simple. Okay? 168 Newton sine is supported in a motionless position by two ropes, as shown, which I don't have the diagram for. Well, I'll draw for it. That each make 22.5 degree angles with the horizontal. What is the tension in the ropes? So let's just draw this here, and then I'll see if you can do it. The weight force is 168. 22.5 degrees. This is tension Y. This is tension Y. I'll let you draw that. Okay, so the question is, what are we trying to find? You're trying to find the tension in the ropes. Why are you looking at me like that, Ray? No. Okay. You're just giving me that, like I'm not speaking English look. Okay. So in this case here, I've got two TYs, and the sum of them must be what? The sum TY, we could call them TY1 and TY2 if you want. Are they equivalent to each other? They are. And the only reason that they're equivalent to each other is because the angles are the same. If those angles were different, would they be equivalent to each other? No, they would not. So let's obviously start with an easy one here, right? So let's say 2TY is equal to 168. Is that okay? If I say that? Which means that tension, the Y component of the tension is equal to 84 newtons. Now let's go into our triangle here. TY, T, 22.5. I've got opposite and an angle, and I want to find hypotenuse. What is opposite and hypotenuse? Sine. Right? So sine of 22.5 is opposite, which is my TY, 84 over hypotenuse, which is T. T equals 84 over sine 22.5. I don't have a calculator. I get 219.5. So the tension in the ropes is 219.5 newtons. If the rating on the wires were, say, 200 newtons, well, then the sign wouldn't stay there very long, would it? What could you do to, let's say the tension in the rating on the wires was 200 newtons. What could you do to the arrangement to allow it to stay up? Yeah, well, it would be increase this angle, right, I guess? Make it more vertical, right? You'd want it more like this. Right? That would do it, right? You're reducing this angle in here, but you're increasing that angle there, right? Depends on which angle you're talking. Make it more vertical. Do you want to try a couple? Anyone? Shall I do one more with you? What's different about this one? It says the sign from the preceding example, exactly the same, 168 newtons, is now hung by ropes that each make an angle of 42 with the horizontal. What force does each rope exert? I think it's exactly the same, except instead of 22.5, you're going to use 42. Go ahead, try that. You can do it. It's exactly the same setup. So let's have a look at this. So all you really got to do is what? A single Ty is going to be equal to 168 divided by 2 is still going to be 84, right? Sine equals opposite over adjacent. So sine of 42 degrees, my opposite.
Isn't that over hypotenuse?
Hypotenuse, thank you. So sine 42 is opposite Ty. 84 over hypotenuse, which is my t. Switch the spots. 84 over sine 42. It's exactly the same setup, right?
Would always be the same formula? Would always be sine?
Well, it'll always be sine as long as you're talking about which angle. This one, if I did it the other way, whoops, I didn't try that very well. But this angle here would be 48, wouldn't it, right? And my Ty would be right here. So if I've got this angle, then the Ty is adjacent, and you'd have to use cosine, right? So I can't say yes always, because if I give you that angle, it's going to be cosine.
Why did you do this?
Because some textbooks just do it that way. They say how much it is from the vertical. They usually give you whatever's the smaller end. Yeah. I get 125.5. Why don't you guys try the second one here? An 8 Newton weight has one horizontal rope exerting a force of 6 newtons on it. What are the magnitude and direction of the resultant force in the weight? And what force is needed to put the weight into equilibrium? In other words, what is the equilibrium? What are the magnitude and direction of the resultant force on the weight? So we've got an 8 Newton weight, so gravity is acting down. And you've got a rope that's attached sideways, or wires or rather, and it's pulling 6 newtons this way, to the right. What are the magnitude and direction of the resultant force on the weight? So you simply add them tip to tail. So you've got 8 and 6, giving you a overall, we'll say, applied force, or it's a net force, I guess, or if you want to just call it resultant, that's fine too. R squared is going to be 8 squared plus 6 squared, and I can tell you right off the top that I know it's 10. What's the angle? Inverse tan of 6 over 8. Not 45, it might be 30, I'm not sure actually. 36, 37 degrees, right? So what force is needed to put the weight into equilibrium? Now, we haven't really been given any references for this angle, right? Like we haven't been given south or east or anything like that. It's really 37 degrees right of vertical. Like this is the hardest. The hardest part of this question is trying to figure out how do I describe that direction, right? And so the equilibrium is simply 10 newtons in the opposite direction, right? So that would be 37 degrees left of vertical. Or if you just said opposite direction. What does E stand for? Equilibrium. E is the equilibrium. Really, the hardest part of this question is figuring out how do I describe the direction. You probably should, but I mean, if you've got a diagram here, then, right, I mean, I'll try to make sure that you don't have issues trying to describe angles. That's quite often the biggest problem. Okay, there's a couple more to try. There's 3 and 4. I have an appointment in the morning, and I'm not sure when I'm going to be here. It might be 9:15, it might be 9:30, it might be 9 o'clock, I'm not really sure. So tomorrow, try 3 and 4. Do you want me to do the solutions for 3 and 4 and just go to leave them for you?
We know the solution.
Oh, you do?
Yeah, that's right. We have picture day tomorrow too.
Oh, tomorrow's picture day, right? Okay.
Tomorrow's the work.
And you're not here tomorrow, right? And someone else. You're not here tomorrow, right? Okay, so work period tomorrow. Start with 3 and 4, and then you've got some other ones to work on there, and then I'll be back by then for sure. Okay?
You want to start?